Hi class, welcome again to another session on biomaterials. So let us now discuss the last topic of our second unit that concerns with metals. So after this, we shall move on to ceramics. So the last topic, like we have seen what metal implants can do to the human body, like how useful metal implants are. However, one of the major drawbacks of using metal implants is corrosion, right? So when a metal reacts chemically with the environment, it degrades by producing oxides, hydroxide or other compounds. So this unwanted chemical reaction, if it's a wanted chemical reaction, if it is something that was done on purpose, then it's okay. But if it is an unwanted chemical reaction, then it comes under the category of corrosion. So we know that our extracellular fluid, our intracellular fluid, or the tissue fluid has got a lot of electrolytes in it, right? So there are chlorides, hydroxides, iodides, and all sorts of all sorts of ions present in the body, right? So this makes the body fluids extremely corrosive. So metal loves to react, right? That's why it's metal, right? It's got a lot of free electron in its valence and in its conduction band, which is always, ready to react with a negatively charged ion and settle down, right? So metal, when a reactive metal comes in contact with the body fluid, it reacts aggressively because the free electrons would like to form bonds with the negatively charged ions and then enter a stable state. So this reaction results in a compound that would ultimately lead to the corrosion of metal. So corrosion occurs when metal ionize and react with oxygen or other molecules present in a solution to form a compound that flakes or dissolves. So either it comes out as flake or it dissolves completely in the fluid surrounding it. So if we look at an electrochemical cell, we know that cells have an anode and a cathode. So if anode is a metal implant and cathode is the electrolyte and the electrolyte is also surrounding it. So at the anode you have the metal that is leaching and becoming a metal ion and it is releasing some electrons, right? So at the cathode, either the metal goes and collects the lost electrons and becomes a stable metal. The metal ion collects electrons that it has lost and becomes a stable metal. Or the metal ion reacts with the hydroxide and forms metal hydroxide. Or you have the H3O ions that react with electrons and release hydrogen and water. Also, you have the reduction that is going on. The water is reduced to hydroxide ions. So, at the anode, there is oxidation that is occurring, and at the cathode, there's reduction that occurs. So, if two dissimilar metals are present in an environment that has more than if there are two dissimilar metals, right? For example, you have an implant which is made up of metal A, and then for some reason the extracellular fluid has some metal B, right? So the one with the most negative, the one that is most negative in the galvanic series will become the anode, and the other one is becomes the cathode, right? Now you have the Pourbaix diagrams for corrosion. So this actually specifies the regions where the metal is corrosive, the region where the metal is passive, and the region where the metal is immune. So now all these depend on the electrode potential and the pH of the fluid that is surrounding the metal. Now these are derived from Nernst equation, the solubility of degradation of products, and the equilibrium constant. So this diagram is derived based on the Nernst equation, then the solubility of degradation of products, and the equilibrium constant. So the immunity region, as the name suggests, is the region in the diagram where the metal is not attacked by the surrounding fluid, right? Passivity occurs when metal forms a stable oxide coating. So, like formation of aluminum oxide on surface of aluminum, alumina. So that is aluminum oxide is very stable. Aluminum as such is quite reactive, but it reacts vigorously with oxygen in the atmosphere and forms alumina, which is very stable. Corrosive phase, on the other hand, is the phase where the metal is actively attacked by by the surrounding fluid. So this is the phase where the metal aggressively reacts to the ions present in the surrounding fluid and tries to reduce or oxidize. So this is just a sample diagram of sample Povey diagram. So you can see the yellow layer, which is the cathodic protection or the immunity layer. So it's also called as cathodic protection. Then you've got the passivation layer and the corrosive layer. So passivation layer is where you have the oxide layer forming the protection layer that is formed, and corrosive layer is where the metal reacts vigorously. So this is a graph that was plotted against the plotted like pH against potential. So rate of corrosion and polarization curves. So Povey diagram just specifies the region where corrosion is going to occur. However, how quickly the metal is going to get corroded depends upon the rate of corrosion, and that again depends upon the electric current density, which is predicted by the polarization curve. So these curves help in calculating the number of ions that are released per unit time and how quickly a particular metal is going to flake away or going to corrode. So that is the overall weight loss of the metal. So the rate of corrosion also depends on synergistic factors such as uneven distribution of mechanical strengths. So the stressed alloy failures occur due to propagation of crack in corrosive environment. For example, if there is a small crack in your implant, then that results in uneven distribution of stress along the surface of the implant. So that would further enhance breaking of the implant, and it would further aggravate the fracture. So this is the corrosion fatigue. So, for example, corrosion fatigue or repeated deformation of the metal in corrosive environment results in acceleration of both corrosion and fatigue micro damage, which means like if there is a crack, then corrosion is like very active around the site of the crack, and if this crack becomes larger with more mechanical deformation, larger the crack, more corrosion occurs, and it's like a positive feedback that is occurring. So, since body environment involves both repeated mechanical loading and chemical aggressive environment, like you don't have just because there's a crack present in the implant does not mean that the extracellular fluid is going to excuse the crack, right? So, if there is a crack, more and more fluid is going to get accumulated around the crack, and that is going to facilitate corrosion. At the same time, just because there's a crack does not mean that the body is going to understand and not put enough mechanical load around the implant. It's not possible. Unless you are in pain, you are going to, continuously put pressure on the, provide mechanical load to the implant. Once you are in pain, at the point at which the person is in pain would have resulted in quite a lot of damage to the implant. It's irreplaceable, irreparable. You have to have corrective surgery by then. So, presence of crack as well as mechanical loading and chemical reaction is going to occur, and presence of crack is just going to facilitate the damage of the device, like or the corrosion of the device, and it's just going to accelerate the process. So the most commonly observed corrosion are fretting. So fretting means just formation of a small bumps around the surface of the material. Pitting corrosion means formation of pits, small holes around the corrosion, and it's commonly formation of holes around the metal, and that is commonly observed in stainless steel. So localized corrosion is generally observed around the grain boundaries, and then crevices is like due to different crevices occurs due to difference in chemical environment. It's just like, flakes of metals, coming out of the surface of the implant. So bone screws and bone plates often suffer crevice corrosion because they are constantly exposed to tissue fluid around the bone. So that would result in slowly flaking of the implant, and that can weaken the implant, and ultimately, uh, the implant would crack because of mechanical loading and loss of weight. I hope you had a good session learning about corrosion with me. That's all I have to say for this video. I shall see you soon again in the next one. Thank you very much.